Hello dear friends, welcome to the lecture of linear algebra. We are studying vector spaces. Earlier we have studied linearly dependent and linearly independent vectors. In this lecture we shall study basis of a vector space. I have written the definition. The definition is a subset. A subset S of a vector space V is called a basis of V if S consists of linearly independent elements and V is equal to L of S. Means there are two conditions for basis of a vector space. First is the basis consists linearly independent vectors, and the second is the linear span of the basis set must be equal to V. So V must be equal to linear span of S. That is the second condition. We shall consider example for this. Let S be the set containing the elements E1. E1 is 1, 0, etc. up to 0. That means we are considering the vector space Fn. E2 is 0, 1, second element is 1, remaining elements are 0, and these are n elements total, and so on. En will be all elements will be 0 except the last one, and each will contain exactly n elements. Let S be the set containing these number of elements in the vector space. This vector space we have denoted by Fn, or we may say as Rn, or this may be taken as Rn, n dimensional, because every element or every vector is having n components, n tuple, and this is the set. We shall show that this spans Fn. Now first thing is E1, E2, the set. This set S is equal to E1, E2 up to En is linearly independent. This we have shown earlier. This set is linearly independent. It is easy to show. Alpha 1 E1 combination of these, alpha 1 E1 plus alpha 2 E2 and plus so on, plus alpha n En is equal to 0. That implies each alpha must be equal to 0, and therefore this set S containing E1, E2 up to En is linearly independent. Second thing is we have to show the first condition is first condition holds. Now what is the second condition? V is equal to L of S. Here V is Fn. Now we have to show that V is equal to V here is Fn, n dimensional vector space is equal to L of S. To show this equality, we know the linear span is always contained in the entire vector space, because linear span contains the linear combination of these vectors, and these are the vectors in again Fn, and therefore its linear span is in Fn. Obviously, or we have L of S is subset of Fn. We have to show the equality, we have to show the remaining part or the converse, that is Fn is contained in L of S. Is subset of L of S. This we have to show. Now for that purpose, let an element in Fn means it is a n tuple. V will have n components V1 up to Vn, or we may consider V1, V2 up to Vn. This belongs to Fn. And we have to show this V is contained in L of S. That means V is the linear combination of elements of S. So this V can be written as, so we can write V as, V is equal to, say, V1 in the vector V1 multiplied by the vector 1 0 up to 0 plus V2 multiplied by the vector 0 1 0 0 and so on, plus Vn multiplied by the vector 0 0 1. See, this is obvious because this will be V1, all other remaining components will be 0. This is 0, V2, second component is V2, and the next third component will be V3, remaining all will be 0, and in the last component is Vn. So we get exactly this as V1 comma V2 and so on up to Vn. So we have earlier also expressed this type of vectors, and thus but what is this vector? That is E1. So thus V is equal to V1 E1 plus V2 E2 and plus so on Vn En. So what this shows that V is a linear combination of E1 E2 up to En, and that means linear combination of vectors in S. That is, V is subset of L of S. It is spanned by the elements of S. V is expressed as the linear combination of elements of S, means V is in linear span of S, and thus V belongs to, what we have considered is V belongs to F of Fn, n dimension, and V belongs to S means this Fn is subset of L of S, and thus this F of n is subset of L of S, and this proves Fn is spanned by L of S. Therefore, this is subset of L of S. Hence, this is equal because the earlier inclusion holds, and this shows that S is a basis of Fn. S is a basis. Now likewise we can have the basis for see F2, F3 etc. The set we may consider two dimension 1 0 0 1. These are linearly independent vectors, is a basis of F2, two dimension or R2, and the set 1 0 0 0 1 0 0 0 1 is a basis of F3, three dimension. So these are the this is known as these bases are known as standard basis. So we may state here this basis is known as standard basis. There may exist more than one basis, and this basis is known as standard basis. Why? Because the first component is considered as 1, remaining 0, and in the second element the second component is 1, remaining is 0. In this way these elements are formed. So therefore a basis containing these E1, E2 etc. will be known as standard basis. So this is a definition and example of basis. Now we shall state a theorem about basis, which is important. That means if there are two bases or two bases of a vector space, then they will contain exactly the same number of elements. That is the theorem, and this will be our theorem 3 in serial order. So we shall state the theorem as third theorem. This holds for finite dimensional vector space. If V is a and any two bases of V have the same number of elements. This is the theorem. So how to prove the theorem? We will assume that there are two bases of V, and then we shall show the two bases will have the same number of elements. So we shall prove the result now, or the theorem. Let S1, we will assume the two bases as S1 containing the vectors V1 up to Vn, or V1 V2 up to Vn, and S2 containing the vectors W1 W2 up to Wm. Be the basis, be the two bases of V, of the finite dimensional vector space V, finite dimensional vector space, yes, it is V, and these are the two bases that we have assumed. Now what we have to show, these two bases contain the same number of elements or equal number of elements. That means here how many elements are there? N, and here m elements are there, and they are two bases of V. We have to show that n is equal to m. So this we have to show. N is equal to m. Now for that purpose we shall see S1 is basis. S1 is the basis of V, and W1 is element of V, because S2 is also basis of V. Both span, both are basis, means by definition these are linearly independent. S1 is linearly independent, S2 is linearly independent, and V is equal to L of S1, also V is equal to L of S2. Both of them span the vector space V. So we shall consider V is equal to L of S1, and W1 is an element of V. So what that will imply, that W1 can be written as the combination. Meaning of basis means every element of the vector space is written in terms of basis elements, as a combination of basis elements. So that's why it is called basis, and therefore W1 can be written as linear combination of the elements of S1, which is V1 V2 up to Vn. So that we shall first state. See, we have now V is equal to L of S1, and W1 belongs to V. This element is also in V. All the elements are in V because these are S1, S2 both are subset of V, and L of V is equal to L of S1 and W1 belongs to V. Therefore, W1 can be written as a linear combination of V1, V2 up to Vn, and therefore the set we will form the set, say S3, containing W1 and V1, V2 up to Vn. Is this also span also span V, and this set is linearly dependent. Why it is linearly dependent? Because if it is linearly dependent because W1 is expressed as linear combination of V1 up to Vn. This is a basis, and any element of W1 is an element of V. So therefore, W1 must be expressed as linear combination of V1, V2, Vn. And now you see, therefore the set W1, V1 up to Vn will be linearly dependent because the first vector is linear combination of remaining vectors. Then the set is linearly dependent, and V is spanned by S3. The linear span of S3 is again V because S3 contains V1, V2 up to Vn, that is S1, and V is spanned by S1. So therefore, V is also spanned by S3. Since further, see, S3 is linearly dependent. S3 is linearly dependent. One vector of S3, say Vi, one member of S3, Vi of S3 can be written as linear combination, as a linear combination of preceding vectors. What will be the preceding vectors of Vi? See, Vi not equal to W1. So, one member Vi which is not equal to W1. W1 we should not consider because W1 single will be linearly independent, and therefore one member Vi, we can say one member Vi not equal to W1 of S3 can be written as a linear combination of its preceding vectors. And what are the preceding vectors of this? V1, V2 and so on up to Vi minus 1, preceding vectors of Vi, and thus therefore the set we thus form this next set as S4. Therefore the set S4 formed by this combination, formed by these elements, not combination but the elements. Then the set S4. Now what we will do is Vi we shall delete from S3 and form the set S4. The set S4 which will be W1, V1 and Vi minus 1. Vi plus 1. That means Vi is deleted. Write V1 up to Vi minus 1, then delete Vi because Vi is again linear combination of V1 to Vi plus 1, and then continue it up to Vn. So this again spans the vector space V. So we will span the vector space V. So thus S4 is again a linear span of S4 is again V. The vector space V is spanned by S4. Now next we shall see this this is a linear span, or that is it spans the vector space V, means that is V is equal to L of S4. It is a linear span of S4, V is. And now we consider the next vector of S2, that is W2. Earlier we have considered W1 and we have formed S4. See the procedure. What we have considered is S1, V is a linear span of S1, and then W1 is considered. So W1 is expressed as linear combination of V1, V2, Vn, and therefore W1 plus this set becomes dependent, and it again spans V. And in this linearly dependent set, one member, so this is actually a theorem second. You should refer what we have written. If the set is linearly dependent, then one member of it, that is Vi, one member of this except W1. So the Vi not equal to W1 of S3 can be written as linear combination of its preceding vectors, that is V1 up to Vi minus 1. This is theorem second we have proved. So you may refer it. If in a linearly dependent set, one member is written as linear combination of its preceding just earlier members, and therefore now we delete Vi from this and write the set S4. Now what the set S4 will be from S3, W1, V1 all will remain except Vi. Vi is deleted, and this again span V, because Vi will be written again in terms of V1 up to Vi minus 1, and therefore this set spans V, or V is equal to L of S4. Next W2 belongs to V, and therefore W2 is a linear combination of these vectors, and the set therefore W2 can be written as a linear combination, of elements of S4. Why? Because S4 spans V, and therefore any element of V, W2 is an element, can be written as linear combination of this, and then the set S4. Then the set S4. Now what we will do for the set S4, we will add W2 in this. Then the set S4 is equal to W2, W1 and V1 up to Vn. So W2 next we have considered. First we have taken W1, now we have taken W2. Now is linearly dependent. Why? Because W2 is a linear combination of the remaining vectors, therefore this becomes dependent, linearly dependent, and V is spanned by S4. Again, since S4 is linearly dependent, one member of S4, and that member now we will denote by Vj, because Vi is denoted, we have denoted Vi as member of S3, we shall denote Vj as member of S4. This is notation. One member it is denoted by the notation. One member Vj of S4 can be written as a linear combination of its preceding vectors, and then this process continues. The vector space formed by, now it will be formed by the next vectors next set will be formed by S5. So after expressing Vj in terms of earlier vectors, that is preceding vectors, we can rewrite the set S4. Then the set of 10 will form. So Vj of S4 can be written as linear combination of its preceding vectors. Then the set obtained set S5 obtained from S4 by deleting Vj. Delete Vj from this and we will get another set S5 will span V, will span the vector V. So thus we continue this process. We continue this process of deletion of W and not W, deletion of V and inclusion of W. So first we have considered W1, we have included W1 in this set and we have deleted one Vj, Vi. Then we have deleted one another Vj. So delete Vj and this W2 is included. So this process, we continue this process. This process of exclusion of an exclusion of a V and exclusion of V's and inclusion of a W in each step. So we continue this process of exclusion of a V, that means one member of V, and inclusion of a W in each step. Then we will replace these V's by W's. So this the set S1. Further, we have to state that the set S1 will not exhaust before S2. In this process, the set S1 will not exhaust before the set S1 of V's. The set S1 of V's will not, the set S1 of V's will not exhaust before the set S2 of W's. See here, S1 is the set of V's and S2 is the set of W's. So we have in first step we have excluded one V and included W1 in this set. In the second step we have included W2 also in the set and we have excluded another V. First we have excluded Vi, here we are excluding Vj. See, Vj, one member Vj of S4 can be written as, and we exclude that Vj, delete this Vj, and the remaining set will again every time it will span V. So this is the process. That means exclude V's and include W's. So this set, what we are writing is, in this process, this set S1 of V's will not exhaust, means it will not over before the set S2 of W's. So when it will over, if it contains less number of elements than the set S2. So that means if S1 contains, say, V1 up to V8 elements, and S2 will contain W1 up to W10 elements, then in the replacement of V's by W's, so this will over exhaust earlier, because there are 8 elements, there are 10 elements. So this will happen. But if this happens, then this V will be spanned by a subset of W. So only 8 elements will be there in the newly formed set. So will not exhaust before the set of W's, otherwise V will be spanned. V will be spanned by a subset of S2. See, if it is over earlier, then some W will take place of V's, and that will span the entire vector space V. And if it spans the entire vector space V, then S2 will be dependent, linearly dependent set, because its subset spans the vector space V. And then S2 will be linearly dependent. So therefore this will not happen, because it is linearly independent. It is a basis. S2 is a basis and it must be necessarily independent. So this what we are writing is important. In this process of replacement of V's by W's, V's will not exhaust, will not over earlier the of W's, because if that happens, then this W will take place of V, and few W will not be included in S1, and that is a subset of S2, and subset of S2 forms spans the vector space, and then that means S2 will be linearly dependent. So therefore this will not happen, so will not exhaust earlier, and therefore this N, this will not exhaust earlier means these numbers are not less than these numbers. Just we have written 8 elements, then 10 elements. This will not happen. So therefore N is not less than M. Hence, or thus, N is not less than M. This will not exhaust earlier means this will not over. These number of elements will not over earlier, and thus N is not less than M. So this number of elements in S1 is not less than the number of elements in S2, that we have proved. Now what we shall do is we interchange the role of S1 and S2. Interchange, that means in place of S1 consider S2, and in place of S2 consider S1, and repeat the same process. And in that way we will prove that M is not less than N. So interchanging the role of interchanging the roles of S1 and S2. We can prove, or we can have, M is not also less than N. So just it is a convention, we have taken S1 and S2, we can interchange it. So M and N can be interchanged, and similarly we can get the second result as M is not less than equal to N. In that case what we have to write W's here and replace W's by V's. So in that case M is not equal to N, and what both together imply, N is not less than M and M is also not less than N, means they must be equal. Hence n is equal to m. They are not less than each other, means n must be equal to m, and if n is equal to m, the theorem is proved. That is what we wanted to prove. This is a basis and this is second basis, and the first basis and second basis will have the same number of elements. Any two bases of V have the same number of elements. This proves the theorem. So thus we have proved that any two bases of a vector space contain the equal number of elements or the same number of elements. An example can be taken as say for this, to show two bases have the same number of elements, that we shall write as example for this. The sets S1 and S2. S1 is standard basis, we shall consider 1 0 0, and S2 can be considered as, say, first element is the same, the second is 1 1 0, and third is 1 1 1, are the two bases of F3. These are the two bases of F3. Now see the number of elements in these two bases. So first contains this S1 contains 1 2 3 standard basis it is for F3, 1 0 0 0 1 0 0 0 1. Any vector in F3 can be written as combination of these three vectors. This example we have seen earlier after definition, that is E1 E2 etc. And this is S2 another 1 0 0 1 1 0 and 1 1 1. So this is also a basis. You may show this forms a basis. To show this forms a basis, show these are linearly independent. And second thing is, any vector v1 v2 v3 can be written as combination of these three vectors. So these are two bases of F3, and these two contains the same number of elements. See, three number of elements, 1 2 3. This also contains three elements, are two bases of F3, and these contain the same number. Same number of elements, that is 3. So you should, this is obviously we have shown this is a basis. Try to show S2 is also a basis. Then they will contain the same number of elements, and that is that will be an example of our verification of this theorem. In finite dimensional vector space over F, any two bases have the same number of elements. Thus we have proved an important theorem relating number of elements in basis, and remaining part we will continue next time. Thank you.